differentiating this expression then, I'm just going to use this expression up here to differentiate. So I need to use the quotient rule. I'm going to get -1 times x squared minus x plus 1 minus -x times 2x minus 1. That's all going to be over x squared minus x plus 1 all squared. Okay, so then I'm going to simplify this expression. I'm going to end up with, it looks like, counting my x's, x squared, so I'll get +2, -1, so I get x squared, +1x squared. My x terms, I get +1 and minus x, so it's just going to cancel out. So then I end up with, in terms of my ones, I'm going to end up with -1. Okay, so that's my numerator, and my denominator works out to be x squared minus x plus 1 all squared. And this is for the domain of x is less than -1. So there's my derivative, and for the positive version, it's just going to be the opposite sign. So we're going to end up with negative x squared minus 1 all over x squared minus x plus 1 all squared, and the domain for this is x is greater than -1. Okay, so then we want to test for where this function has horizontal tangents. So if we take a look at the numerator, which he solves the numerator is going to be for x is equal to plus minus 1. Okay, now at -1, we already have our restriction. So really our slopes are going to be tested for x is equal to +1, and we're going to use this derivative because that one is the one that is going to give us, that is for the domain of x is +1. So I'm going to draw my +1 coordinate. I've got a 0 slope here, and I'm going to just test these different regions then. So I'm going to test for the left side I'm going to test on the positive side first. So let's make a chart here. So f prime at +2. If I plug +2 into there, I'm going to get negative in the numerator, and then the denominator is always positive, so I'm going to have negative slope. So I know I'm pointing down like this. There's a horizontal tangent here at f prime of 0. If I just test the 0 on the left side of that, I'm going to end up with negative, negative, so it's going to be positive in the numerator. Again, the denominator is always positive because it's squared, so I'm going to get that. I should also test the derivative to the left of -1, so I need to use the other derivative. So we're going to test the derivative at maybe -2. I plug -2 into that expression. The numerator is positive, the denominator is always positive, so I get positive slope through here. Okay, so I'm going to end up with positive slope to the undefined point, and then our slope chart is going to look like this. So it looks like I have a max coordinate at x equals 1. So I'm actually going to put that into my list of points. So at x equals 1, plugging into my original function there, I'm going to get 2 in the numerator divided by 4 in the denominator. So I end up with 1/2. So at x equals 1, x equals 1 and y equals, oh, that's not going to be 1/2. That's going to be 2 divided by 2. So I'm going to end up with x equals 1, y equals 1. So then I have a max coordinate here at 1, 1. So now I have pretty much everything I need to graph this expression. I have my slope chart. I know that for this section here, it's going to be a horizontal asymptote. It's going to be going up to that point. We know that it's from the -1 on the right-hand side, it's going up it's going to go through the 0, it's going to go to a max coordinate here, and then it's going to start coming down, and it's going to have a horizontal asymptote coming down here. And we don't have any more zeros, so we know that it's going to follow the asymptote that way. So that's what our function is going to look like. And we've got a number of different parts to consider now. We have points of discontinuity. Okay, we have non-differentiable points. We have lots of things going on that we have to now consider. But the key one here that we have to make sure we understand is that at that non-differentiable point of -1, okay, we have to check for that discontinuity, and we need to also test slopes on both sides.